So for those of you who know me, I'll bore you with a little of my background. So I'm an evolutionary ecologist and a botanist with a focus on rainforests. I work around the world with various organisations on everything from inventory of the flora and sometimes the fauna, restoration of large-scale impacts on landscapes in Madagascar and Southeast Asia. I work with colleagues around the world. We use fossils and fossil locations to explore the origins of Gondwana and the Southeast Asian rainforests and how the Australian rainforests have emerged. So tonight we're going to take a large journey through deep time up to the present, and we're going to explore some of those factors. And it's a thrilling ride. It's an evolutionary ecology story. It's a biological survival story that's almost unsurpassed on the planet. Australia left Antarctica, and we'll go into this in a little more detail, around about 38 million years ago. And as it did, it tore away at around 3.5 to 7.5 centimetres a year and did so for 38 to 40 million years. In the process of separating from Antarctica, it changed the climate of the world and it rafted away with the highest Gondwanan diversity of any part of the Antarctic continent. And originally, of course, it was linked to South Africa, South America, India, Antarctica. So this supercontinent that slowly broke apart from about 110 million years ago, when Africa drifted away, when India started rafting across towards Africa, took Madagascar with it. And the real story for us is from about 70 million years ago, when the Gondwanan history, the Antarctic, South American, Patagonian, Australian, New Zealand story really emerged. In this area of the wet tropics persists some of the most amazing diversity, and that diversity has its origins in that Antarctic flora. It has strong relationships to Patagonia still. That can all be traced through the fossil record, through the geological record, the movement of continents through space and time, and ultimately through the plants that are living here around us in this area and still in Australia, right from the northeast of Australia right through to Tasmania. So it's an extraordinary story, and it's a pleasure to share a little bit of it with you. So we'll start in the Daintree on the lowlands, remembering that just a little while ago, 10 to 20,000 years ago, there were a series of climatic variations that were quite extreme. These were the penultimate ice age variations, and in that process, what was once land all the way out towards the barrier reef was flooded by the ocean. And the consequence of that, of course, was that the vast lowland rainforests and swamp forests that occupied that retreated backwards. But that's recent. We're going to go way, way deeper than that. What I wanted to highlight here, of course, is that within the Daintree rainforest, from the lowland to the upland to the hill slopes, there's an incredible amount of diversity spread through those forests. A lot of that diversity is Gondwanan, but some of it's also Indo-Malesian, has come more recently from Southeast Asia. And so it's those interactions that we want to explore a little more. So even in the Daintree, the rainforest, hyper-diverse, very complex, but in some situations under extreme environmental conditions, it simplifies. And so in this case, you get a dominant palm on a very wet, seasonally very wet, inundated area on poor nutrient soils. So that can happen as well. So there's lots of variation. So currently, we're working on a very large paper which is a synthesis of the whole of the Southeast Asian rainforests, their origin, their evolution and their assembly. The reason we're so interested in that is because Australia, after 38 to 40 million years of rafting away from Antarctica, collided with Southeast Asia. What came from that collision was Papua New Guinea. Papua New Guinea rose up, so we have mountains to 5,000 metres on what we call the Sahul Shelf, the Australian shelf. So Papua is actually part of Australia. So politically, it's not the case, but geologically and in terms of the history of that particular plate, Papua arrived with the collision of Sahul, Australia, with Southeast Asia. So that had major implications for the vegetation, because Australia had rafted away from Antarctica as an isolated continent. It had unique flora and unique fauna, and it had deep time origins to Gondwana. But when it arrived in Asia, it started sharing the vegetation with Asia, and of course, so Asian plants moved into Australia and Australian plants moved into Asia. And all of those reactions were based on climatic oscillations. As Australia moved northward over those 38 million years, the biggest single feature and factor that occurred was that as it left Antarctica, it created the circumpolar current, and that changed the Earth climate. And so the continent of Australia went from being a cool, wet place and a warm, wet place at different times to a much drier continent, and in the end, one of the driest continents on the planet. So the consequence of that drying, of course, was that we lost somewhere in the order of 90 or more % of the rainforest area. So the reality of that was that as we arrived in Asia, we had lost a vast amount of the rainforest already. But as we did arrive, we managed to see some of the plants leap into newly uplifting mountains and move into Southeast Asia, and in fact right up into Malaysia and into China. So this is just to remind you the way the world really looks, right? If you come from the southern world, this is how the world, that is the top of the world, right? So don't let anybody tell you different. The southern world rules. So down in the bottom corner there, you can see what Gondwana and the southern world looked like around about 50 million years ago. And what happened, of course, as you can see, Australia still connected to Antarctica, South America, Patagonia still connected to Antarctica, so no southern current. And that's the big difference. This is in May 2019. There's the southern circumpolar current, and that created a serious ice age. And the consequences of that was cooling and drying. And that dryness was biting at the heels of Australia the whole time it was slowly escaping from Antarctica. And as the cool, dry weather bit at those heels, the rainforest area contracted and contracted and contracted. So we ended up with a very, very different looking vegetation than we started with. We'll talk a little about climate, and see, these are some cool climate questions. Why were the rainforests in those locations? Well, obviously, the combination of high rainfall and the temperature range in the tropics is essential. And that's partly the reason that the Gondwanan forests and the Southeast Asian forests have converged in this area and have survived through time, even some massive climate variations. What shaped those climate conditions? Part of it was the continents moving away, travelling and colliding and causing those mountainous uplifts, Papua New Guinea. India moved away as well from Antarctica a little earlier than we did, about 60 million years earlier, and ended up colliding with Asia and South Asia. And of course that resulted in the Himalayas and a massive uplift. And that changed the whole climate of Southeast Asia. So that's a huge shift. Even Southeast Asia was relatively dry, seasonally dry, and didn't have the rainforest areas that it currently has. So Southeast Asia was dramatically altered by the collision of India with Asia, the uplift of the Himalaya, and that changed also, of course, the southern Chinese vegetation. So all of these things are going on during this period of time. So we sort of need to know what actually warms the Earth climate. And in most cases, it's volcanoes, and more recently, it's us. So they're the two major factors that operate outside of continental drift and major climate changes. But this is something we need to know a little bit more about. What actually cools the Earth? More trees. It's a fairly obvious thing, and we're doing the opposite. We're taking them out, except for today where we put more back, which was a really good thing to do. So congratulations on that. But the other thing that changes the global climate is not just the continents moving around, but it's the wearing down of the continents, the erosion of the continents. So when you get those big uplifts like Papua New Guinea and Malaysia and the Himalaya and all those things, in the tropics, the weathering of those, the erosion of those occurs at a relatively rapid rate. And a lot of those are volcanic basic rocks, ultramafic rocks and mafic rocks. And when they break down through time, They actually create, and the silica rock converts the CO2 in the atmosphere into calcium carbonate, and that accumulates as limestones and things in sediments in the oceans. And there's a massive amount of CO2 stored in those repositories. And that's part of the geochemical cycle that actually controls the tendency for warming and enhances cooling. So these are all things that are of particular interest. But possibly the most important of that is trees photosynthesizing, plants photosynthesizing, and storing carbon. Because when you think about it, everything we do today, our coal resources, our petroleum resources, all of those resources come from the rainforests of the past. So they were all laid down as carbon and compressed through time, and those during major eras of the global climate change, and we ended up with massive reserves of fossilized carbon. And the reality is, of course, now we've reconverted that back into CO2. So a couple of years ago, we answered one of the oldest questions in plant science. Why are the leaves bigger in the tropics? It's the coolest thing in the world when you get to ask a question like that, knowing that Darwin and all of these people had asked this question and no one had ever resolved it. So working with some of the coolest plant physiologists in the world, Ian Wright and a range of other people, we decided to try to work this out using a global data set. And as it turns out, it's not just because there's higher temperature or more nutrients, or it's more even temperatures in the tropics. It's actually because what regulates the global leaf size is simply the difference between day and night temperatures. So if nighttime temperatures are cold and get really cold, leaf sizes are small. And if daytime temperatures are really hot but it's dry, they're really small. But if it's hot and wet and there's unlimited moisture, there's no limit to the size of the leaves other than the potential of the plant to pump the water into the leaf to keep it up. So that only took 200 years. It was quick. Well, it was quick. Yeah, I mean, really, you know. It took us 10 years. So it takes 30 seconds to say that, and it took us 10 years to work that out. So, you know, go figure. So I just wanted to remind you where you were. So here we are, close to Mossman, up in the wet tropics. I don't know if any of you or most of you have taken the drive from here through down to Mossman, up the Gelatin Range, past Mount Lewis, and within 20 minutes, you're suddenly in this dry peninsula country. It's an extraordinary drive and an extraordinary experience. And what it reinforces, of course, is that this little sliver of wet country is a tiny little remnant of what was once a vast area of rainforest. So it's significant. It's really, really significant. And it's very important that we continue to work on it and look after it. So this is just, don't take too much away from this. You can look for as much detail as you want, but the reality is that the take-home messages are clear, that there's rainforests from the north of Australia all the way to Tasmania, and the most diverse rainforest is in the tropical and subtropical north. There's indications there of how many families, how many genera, how many species are in each area, and all of those sorts of things if you want to absorb all that information. The key factor is that the rainforests occur where it's wet. So across the whole latitudinal gradient, there's seasonality, there's all sorts of things, but you've got to have really seasonally wet forest areas. And that's what regulates the distribution on this continent that was once a rainforest continent. So this is really central to understanding what it is that's so important about this area and these spectacular forests and the species that are in them, is that we have ancient rainforests mixing with emerging species in an evolving world. So that's really the incredible story about all of this, that we have these fantastic Gondwanan elements which persist in the Australian rainforest. And in this case, this is a single photograph of ancient Antarctic Nothofagus sitting right next to rainforests with both Gondwanan and Indo-Malesian elements in it, side by side. So one of them's a rocky intrusion on porous soils and the other one's on lovely basalt soils, and it's in that location that regulates that variation. So that's something that we've been exploring more and more, is asking that question, how is the diversity from Indo-Malaysia and Gondwana, how is it distributed across the continent of Australia? So we employed a PhD student, Sam Yap, and we basically gave her our data set, and she's now completed her PhD. And those little pie charts there show you Sahul is of course Australian, Gondwanan, and the Sunda is the Indo-Malaysian influence, and that gives you the proportion of the distribution of the different components in the Australian vegetation. It's a really simple thing, but it'd never been done before. No one had ever actually quantified what was going on and how they interacted. And of course, when you get to Tasmania, it's pure Gondwanan. But there's very few species. There's only 50 species. So even though they're all from Gondwana, you come up here, there's 1,000 or more species, but you can see the sorts of influence. And it's no surprise, of course, that the Indo-Malaysian influence in the north is strong. So that's what you'd expect. So then we thought, okay, and don't get lost in these pretty colours though, I've got to say. Think of this as a family tree. So you take the lifetime evolutionary value of every single species in the Australian rainforest. In other words, your family had father, grandfather, mother, grandmother, great-grandmother, on and on and on, back you go. So if you accumulate all of their lifespans, you're adding up evolutionary time. So that's what we've done for the whole of the Australian rainforest flora, is added up how much evolutionary time is invested geographically around the continent. And so where you see the black are the areas where the deep time is the strongest, the deep time signal. So that the most evolutionary history is embedded in those locations. And again, you can see why the north, the wet tropics and up onto parts of Cape York, and in the subtropic around the Queensland border, there's hot spots for evolutionary history and how much evolutionary time is stored in those places. So that's another way to look at the way the rainforest was distributed. So we then decided, okay, having done that, we should split that between Sunda and Sahul and see how much evolutionary time is split between them. And you can see with Sunda, it doesn't make it to Tasmania, but there's lots of evolutionary time, but the Sahul component of the deep time history is really significant. So we have a lot of species with origins in Indo-Malaysia and from Gondwana, but that mixture is really what's driving it. So what's really interesting about that mixture is that the Gondwanan flora are conservative. So they're not very good at adapting to changes. They actually have a tendency to track the environment that they prefer. So they're threatened by climate change, and significantly threatened if there's no opportunity for them to move. So that's why some of them have jumped into Papua New Guinea, where the mountains are higher and it's cool and wet. And that's why some of them have continued jumping through Asia on the high mountains, Mount Kinabalu, and right up into China to track those climates. The Indo-Malaysian rainforest is a little more adaptable, a little more capable of shifting around. And so this is an example of two species in a genus that we call Elaeocarpus, the blue quandongs, beautiful blue fruits, which are prized, in this case for grandis or angustifolius, is prized by a whole range of bird species who either eat the flesh or ingest the whole thing. This particular fruit dove here, the wampu fruit dove, is capable of swallowing the fruit of a blue quandong, which is about 28 to 30 millimeters. And that's at the top end of what fruit doves and birds can swallow easily, except if you're a cassowary. Of course, you can swallow much bigger fruits than that. I've used the two examples here because one of these Elaeocarpus is an Indo-Malaysian species, which is actually a recent arrival in Australia. So it's only been here for probably less than 1 million years or so, and has rapidly spread along the coast and is heading south, courtesy of the wampu fruit dove. In this area, the cassowary eat that one as well. But there's a closely related species, Sedentarius, which has a sister species in Papua New Guinea, and it doesn't get eaten by birds. So I spent weeks sitting under this tree, watching this thing, waiting for birds to eat it. Nobody visited it, and I thought, wow, what's going on here? But it has a completely different fruit with no reward. The only thing that would eat it is if it fooled the cassowary because it was blue. But in the area that Sedentarius grows in Australia, there are no cassowaries. But in Papua, there are. So in Australia, the species Sedentarius is highly restricted and now an endangered species. But its sister species in Papua is still spread widely because of the cassowary. Even though the cassowary gets no reward, that species has decided, if I look like that, I'll get dispersed. And so that worked. That strategy worked in evolutionary theory until the cassowary went extinct in northern New South Wales, and that was the end of it. So what happens then is that this one gets dispersed and this one gets predated on. The rats love the seeds. So that makes it even more dangerous. And so it's essentially heading for extinction. So that's what happens in the biological world. Some species strategies work, and work sometimes for millions of years until something goes slightly wrong, and then that strategy no longer works. So the challenge for us, of course, is when we look at these sort of species, we look at the range of fruit sizes and seed sizes, and today we planted trees from a whole range of different seed types and fruit types and seed sizes, and some of them were cassowary dispersed, some of them are wampu dispersed, some of them were dispersed by both, some of them are wind dispersed, so there's all sorts of strategies. The wampu fruit dove disperses fruits greater distances. The cassowary is the only disperser of some large fruits. So it's a redundant question. Which is the most important? They're both important, but for very, very different reasons. So now we're getting closer to looking at some trees that don't have fruits. These are the giant Agathis, and this pair grow on the tablelands just near us here. And we did some work on these. Some people have accused us of doing work on these just because we could travel from Patagonia right through the South Pacific, up right through Australia and into Asia, tracing their history, and it's partly true. So it was a great project and an amazing thing to do. But these trees, as it turns out, one of the things that we discovered about the Agathis in the fossil record is when we were working on these guys, and these are wind dispersed Gondwanan conifers. So what we discovered is that they grow nowadays. They once grew in Patagonia but no longer grow there. They're extinct in Antarctica. They're a major tree in New Zealand. They occur in Fiji and a few places in the Pacific. They occur in Australia and Papua, and then right up into Kinabalu and north into Asia. They are Gondwanan, so they're Antarctic in their origins. The closest relative of the fossil in Patagonia we found on Mount Kinabalu. So when we look closely at this, we had to trace the fossil record for the last 70 to 100 million years of the species. And these beautiful fossils were dug up in Patagonia, in Argentina, at a place called Laguna de Honco, which my good friend Peter Wilf curates the site through the Penn State University. And so this paper that we wrote down here actually did something that we didn't quite expect when we started looking at Agathis, is that by looking at the fossils of Agathis, we discovered that they were a major component of the original Antarctic forests. So that had never been understood before. The fossils had never been complete fossils, and no one was ever able to verify it. So one of the things that we were able to do in this paper was, for the first time ever, to describe the history and what the Antarctic forest actually looked like, which is a pretty cool thing to be able to do. So this is what the area looked like when we shared those fossils. Laguna de Honco there in southern Patagonia, Australia still largely connected to Antarctica. And around 52 million years ago, we were in a hothouse. We had tropical conditions in Antarctica. Get your head around that one, right? In the Eocene, there was tropical type forests in Antarctica and Australia, the Zealandia component of New Zealand, and southern Patagonia. So that's an extraordinary shift from what subsequently happened. And that's the origins, if you like, of the major story here, which is the clues that we got from looking at this cowrie, the Agathis, and its movement in the fossil record across half the globe, and its living relatives now in Asia. And so the journey begins for Australia as it begins to shift away, and here we're already 8 million years into the journey, heading for Southeast Asia. India is already starting to make contact, but hasn't started to uplift the Himalayas yet. And Patagonia is just barely separated from Antarctica, but the southern current, the circumpolar current, has commenced. And so the global climate is beginning to change. And at 30 million years, that little gap between South America and Antarctica allowed the current to move through, and the moment it did, we went into massive ice house conditions. The southern hemisphere froze over. So that freezing was chasing Australia north. So the Great Escape story starts. Just to remind you, the circumpolar current. So this is a synopsis of that story, that Sahul, Australia, carried the Gondwanan flora, all of those lineages that were linked to Patagonia and Antarctica, all the way to Southeast Asia. And it's one of the greatest biological survival stories of the planet. So these forests that we visit, that we sit in, that we look out over, carry that history in their makeup, in their relationships with the flora and the fauna that surrounds them. All of that history is packed into these guys. These are survivors. So it's a slow motion escape. So if you're looking for a thrilling ride, you're in the wrong place. But nonetheless, it's an extraordinary process of movement. And for some of the lineages that were living in Australia, of course, at the last second, they jumped from North Queensland into Papua New Guinea, and they went extinct in Australia. So there's a whole slew of those as well. So just to give you a visual of that, there's Antarctica in the Cretaceous about 60 to 70 million years ago. There's Patagonia at the same time, so reasonably close together. This is the whole of the Southern Hemisphere's fossil record that we've put into one paper in one place. So we got people from all over the world to come together, every museum in the world to provide the paleo history, the fossil record of the whole of the Gondwanan flora. So this is a brief history in time. So New Zealand, of course, out here, started off in right field, way over there, and just got weirder as time went on. So around 60 million years ago, we get good records in the fossil record, and we get good records in the Australian record. But Antarctica and Patagonia, there's good, solid records way before then. So Antarctica made it through to the Paleocene, Eocene, and then everything went extinct. So basically, the lights went out on the vegetation entirely. Patagonia, similarly, it survived almost intact with a Gondwanan Antarctic flora with no issues at all. Australia, similarly, we moved from the Paleocene, Eocene into a more recent time, which is about 30 million years ago, as I showed you, and we retained most of that vegetation. New Zealand, there was a supercontinent off our east coast called Zealandia, and it went underwater. So as it went underwater, it lost its original vegetation, and there's probably a couple of little mountain peaks that survived. And so it converged somewhat with the Antarctic flora in the middle there, but then it lost its flora almost completely. So the consequence of that, of course, is that New Zealand is very different now than it was. So Patagonia in the Neocene, Eocene, around that same time, 30 million years, the Ice Age caught it. Southern Patagonia got caught. We were creeping away, so Southern Patagonia had the same sort of flora as Australia, and it was doing really well, and all of a sudden the Ice Age just slammed it. And so it lost most of its Gondwanan flora. New Zealand just got weird again. So it decided it wanted to look like Australia, and then no, that's not a good idea at all. So it decided to go off on its own. So it's now been colonised by all sorts of bits and pieces from the Pacific and from Australia. Australia, right up to the modern time, despite losing more forest almost than any other place, 99%, actually didn't change a great deal. So what that tells us is that despite losing huge amounts of forest, Australia still retains more of the original Antarctic Gondwanan forest than any other place on Earth, right? So that's huge. That's huge. So if you look at that, and of course Patagonia continues, that's the extinction line there. So Patagonia lost almost all of the original Gondwanan flora, but it has the best fossil record. So Go figure. So that's what it looks like when you put it all together, and you look at the relationships of Australia to Papua New Guinea, New Caledonia, Mount Kinabalu and Fiji, where there are strong signals for the original Gondwanan flora. Australia still has the strongest signals of any of those original Antarctic floras. So that's a remarkable thing to have happened, that we could go through those massive changes and still retain the most diversity of that original Antarctic flora. And that's partly what we see around us here. So again, just in case you thought eucalyptus was uniquely Australian, I have to tell you that we have fossils in Patagonia from 52 million years ago, and that we shared eucalyptus with the southern world and Antarctica. And so the fact that they're now here and in parts of Papua and Asia is just a legacy of that incredible biogeographic history. So we're not so unique after all. This is another one, the casuarinas, the she oaks that we see around. This is the earliest relative of those, gymnostoma, and they occur on Noah Creek and up on Thornton Peak, up here in the wet tropics, and up in Asia, and also in Fiji. That's a primate sitting there on the creek. That's me looking across at gymnostoma, right? And so I just wanted to show you my nearest relative. And they're sitting in a gymnostoma in Sumatra, right? So at high altitude, and they eat the seeds. So these are extraordinary connections that we have from flora and fauna. So on that note, this is a picture of Mount Kinabalu, close to the peak, just on the forest edge. And we got, about an hour later, we got 500 millimetres of rain. So it was an extraordinary night. Freezing cold, more rain than you've ever seen, about a metre deep of water rushing off the mountain at you. It was just an amazing place to be. But all of that said, I just wanted to remind you that the wonderful work that Rainforest Rescue does in this area, and the reason it's so important is embedded in that narrative. So many thanks for that.